Sebastian, tell us a bit about your role in the project and give a brief description of the structural framing.
So I'm structural engineer, and I'm looking after the structural engineering business unit for WSP in Cape Town. And so we in 2017 we teamed up with Stefanuti Stocks to bid for this formidable body shop, and started relatively early with a very detailed bid submission design. Leon is one of our principal associates and also structural engineer, and he was instrumental to the detailed design and the modeling and the running of the project. So I'm going to do a short introduction, and then I will hand over to him and give him the opportunity to show us some of the details that we use. But yeah, thanks Leon for sharing the screen. So what we did in preparation of the project, or that detail of model is obviously during the execution of the project. But we went fairly far with a fairly detailed look at how to build the building, and the role of structural steel in this delivery was part of the deciding factors, I think, in us winning the bid in the way less the way we designed it, but more like how we programmed it. And the focus of this building is actually the super high load design of the first floor slab. So it's basically a warehouse, but on a suspended floor. So you got an excess of 40 kPa of live load on that floor, so 4 tons per square meter, on a 14.4 by 18 meter span. So that demanded a incredible amount of thinking. How do you construct a concrete structure like that? We ended up with a precast, with a half precast kind of system, which required handling of very heavy elements. So what we decided to do is to allow the primary concrete beams to run ahead in the program and construct the steel roof on top of them before completing the rest of the concrete structure. So the primary beams and the steel were basically leapfrogging the construction of the first floor slab. And that enabled a system of like basically staged or shifted working inside the space, and also allowed us to handle the craneage efficiently. I'm not sure, Leon, if you have a photo that you can share how that looked. I had to get off the VPN, unfortunately, because Zoom didn't like it, so I don't have access to my photos now.
I do have access to photos. I just want to see quickly how I share my screen.
I've got some photos that were submitted, which I can also share if you want. But that's
let me know if you can see the photo now. I just changed it from program share to screen share.
Okay.
Okay. Okay. What you see here is the 10 meter or 10.5 meter high column and beam construction progressing. So you see the primary beams running ahead. It's like a half precast, half in situ beam, and then the steel is being built right on top of that, and then the slab filled in later. So that actually unlocked the program that made us, or like our team, to win that turnkey bid. And obviously that's it's only possible to do this with the lightweight steel. and at the same time, we needed a lot of it very fast. So it was designed very modular. So I'll hand over to Leon now, who can talk us a bit more through the actual design details.
Okay, super. Emmanuel, just before Leon takes over, you had some questions yesterday about the concrete with the little voids in. Do you want to just ask about that?
Yes. So someone tried very hard to make concrete look like steel. So my question was, why wasn't it just steel?
Which are you talking about? The big beams down here, or
yes. the girders? Yes.
Okay. Well, the loads that we are looking at here, as Sebastian mentioned, we've got a loading of 4 tons every square meter.
Yes.
Just think about that number quickly.
Yes.
There was really no way of doing this structure in steel unless you increase the floor depth as a whole, which we could not do due to everything that was planned, how it's tying into the building next door and the surrounding surfaces.
Yeah, so if I understand correctly, this is a girder in either on top of which or into the web of which you put in some precast planks. Is that correct?
No, not entirely. Let me quickly open an alternative model that contains more of the concrete.
Yes.
Emmanuel, we could have most certainly done this in steel, but you would look at a made-up box girder. Yes. Probably a 2 meter wide and 60 millimeter thick bottom flange plate, and maybe 30 millimeter thick web plates. It would have been probably out of the capability of manufacturing this in a normal steel workshop. You would look at a marine offshore type skill set, and I think, and then also the size of it. They're 14 and 18 meter long, and the 18 meter long, we need 300 of them. So we actually cast these very close to the side.
Yes.
You would have to truck them in from Durban. Yes. Or so like the whole logistics around to make these huge elements in steel would probably not have been possible.
The logistics is definitely one thing, but what we can't ignore here is also, shall I say, the inherent stiffness of the concrete structure. So there was a lot we needed to do here in terms of deflections and stability for the very sensitive robotics that are housed in this building. So while steel is great in terms of its strength, it's not as stiff because you're using such small quantities. So you would have opened yourself up to possible vibrations in the building. You can think there are thousands of robotics in this building, moving around, stopping, starting again. And all of these could actually sync up and cause some real problems for us with the first floor structure.
No, my question was related to the fact that the shapes all look like they emulate steel shapes that are rolled or plate girders. So I thought,
To give you an idea of the shape of the primary beam, the bottom flange is 2 meter wide and 600 millimeter thick, and the web is 1.4 meter wide.
Yes.
And the whole beam with a completely casted is 2 meters deep.
Yes.
So it's actually an incredibly heavy beam, and believe it or not, the shear at the supports is approaching the allowable limits of concrete design. So it's these things are really heavy loaded on top of everything. And
so you guys cast them on site like precast, and then you loaded them onto some conveyor system or truck and brought them and put them up with a crane. Is that right?
Correct.
You can see the bottom flange here shown. That is the the precast site was 500 meter next to the construction site. We were very lucky to get that. And then, but even that thing weighed.
That was 40 tons.
40 tons, yeah.
Yes.
So yeah, you
so
can create these, and then after that we took them to site, and they were then placed on the beams. But your observation saying that the shape does emulate a steel plate girder or a truss in some manner is very accurate.
Yes.
One of our primary goals for the project as a whole was looking at the amount of repetition we've got here. So every element, there's not just 1 or 5 of them. I mean, there were 98 of these primary beams. There were 300 of the secondary beams. So when looking at the detailed design from my side, I tried to make sure that every element was as optimized as could be. And when you're looking at steel construction, this is exactly what we typically do. Yes. Every web member is actually what it needs to be. We don't just put in one typical throughout, and we try to look at the same approach in terms of the concrete and the whole structure to limit the quantities to what we need. So if you're looking at these secondary beams as an example, they started out as pre-tensioned beams or post-tensioned. So we needed the wide flange just for lateral stability while stressing it, so it doesn't just buckle. Later on, it was changed to a conventional beam, not post-tensioned anymore. And in that case, we actually needed the entire bottom flange to fit in the bottom rebar.
Yes.
And that's how it all developed.
Yeah, I bet you there's quite a bit of steel in there, so I'm not complaining.
Yes.
Yeah, you bet.
Just curious. Yes. Okay. Cool.
But if let's take it. Let's pick up your initial question. If we had built this structure in the Durban harbor,
yes,
we would definitely have approached the local heavy steel specialist and say, look, can we actually put a plant on site and make box girders? What is the cost?
Yes.
So it would have been a very interesting consideration, but you need to speak with people that know how to weld thick plates fast and reliably. And
yeah. What I had in mind actually when I saw the project, that was the first thing that struck me. And thanks Denise for reminding me actually, because I had forgotten that was my question. Because we were discussing it, and I had seen another project similar, and in that case what they had done were tubs, steel tubs, plate tubs with studs in them, and it was a composite construction. So essentially the tubs were light enough to get into spot, and then you would pour and essentially the way you would do bridges, let's say in the US or Europe, not in South Africa, but the studs would be welded onto the tub, if you can imagine like a bath tub.
Yes.
So that's actually what we were discussing, was how would you do this in steel, because we knew a plate girder would not necessarily be maybe heavy enough, so it would have to be something composite.
Very interesting. So the benefit out of the steel here really is its nimbleness and its ability to dance around the heavy concrete structure, to stay out of the way, to do its job, to run ahead with the program, and then let the heavy stuff happen after.
So when you were installing on top of these precast pieces, how did that work, the interface?
What we're doing with all our warehouses, we like to start from a strong column framework on the perimeter of the building and build from this inwards. So the concrete columns are actually cantilevers with a strong base. So we no matter where we start, we have a braced corner. We're not relying on steel bracing to be in place, and this is also over 20 meters high. So the same here. We start from the stable corner, and then you see the internal columns are all very light steel sections. There's holding down bolts cast into the into the beams. So they're just placed on the normal holding down bolts, and then.
Okay. So those were cast in with the precast. Or were they cast in when you did the final grouting?
Holding down
with a portion of the precast beams. I believe I did share some drawings. Let me just actually get that one quickly, which shows that detail very nicely. Denise, it wasn't the package that I shared with you, so you guys should have access to it as well. just for future reference. Let me quickly grab that for you.
Because that's very interesting. What you've done here is essentially a combination of precast and steel at different levels, so that interface would have to line up somehow and make it, unless you did a survey afterwards.
No, it was all planned to fit perfectly.
Right.
Just get to the right screen. Sorry, virtual screens for working from home. So yeah, you can give an idea of what that interface looked like. So there's a lot of things happening, of course, but essentially the important bit for us is when we cast this in situ portion of the primary beam, the yellow mark, we had the holding down bolts cast into that portion to take the steel columns. But in addition to that, we actually also included some rebar that you would see on this side. So these white twos were also cast into the beam to then later lap with the encasement that we did of these steel columns. So that was to increase the increase the stiffness of the end conditions for these columns. We tried to keep the columns as light once again as possible to save as much material as we can throughout. So therefore, it was quite a thin column. It was a 406 178, which is quite slender around its one axis. So at the top, it's great. It's tying into the girder for us, but at the bottom, it was basically a pin connection. We didn't go too crazy with the stiffness, just because there was so much steel in the slab that had to come through as well, as you'll see here, with dedicated slots cut through it for this rebar to actually be threaded through. So that way, we decided the way to increase the stiffness here and make the column work is we encase it in concrete afterwards. So it was quite a process to get all of that right as well in terms of the technical details.
So was the encasement designed as a composite, and did it also have a contribution for fire, or was it not such a consideration?
It wasn't a fire consideration for us. It's definitely, there's a benefit for the bottom if fire was to break out on ground floor level, but it wasn't part of the decision that went into it.
Okay. It has a robustness benefit for the operational space. So bumps by materials handling equipment and so on would not really be a concern anymore.
Yes. So there is a composite steel structure, a precast structure, and then a bare steel structure here.
Correct.
Yes.
Okay.
We like to play.
Yeah, I can see. Cool. Very nice.
Speaking of playing, one of the really cool bits for us as well is at some point during the project, when we got to the detail design of some of the smaller bits, we realized that there was no way for us to actually construct the perimeter columns in concrete next to the vehicle ramp in the one corner of the building. So we had to come up with another idea, and we ended up doing these braced lattice columns, as you see here.
I see. Yes.
So these were then made in steel, shipped to the site from Durban as well. And instead of trying to put formwork up there and get a stable concrete column, we put up these quite massive steel lattice columns.
Yes.
Which was quite unusual. As far as I know, you are the man who wrote the article about concrete filled hollow sections.
Yes.
That you say warehouses should be built from, which we have not yet found an opportunity to do, but this is the closest we've come for using big proper steel columns in warehouse construction.
Yeah, that's what I've been trying to work on for the past 2 years, is trying to move away from the concrete columns onto those concrete filled tubes.
Any success yet?
Sorry?
Have you had any success with that yet?
Yes, so there have been 2 projects, and one had no rebar, believe it or not. It did not require rebar. It was about 16-meter height. There were the other ones, of course, that you might also be already familiar with, that had rebar in them. Those were not warehouses. They were actually architectural. What I mean by that is it's Menlyn Square, you know, the big arena, the new arena. I don't know if you've been there yet in Pretoria.
That's our college, I imagine.
Yes, and the Twisty building. I don't know if you've seen the Twisty building in Midrand, the one that twists.
Oh, yes.
Yes.
Yes,
PwC.
that also has yes. So that
PwC.
building also the twisting columns. So what's interesting is of course the architects are all doing slanted columns, and there aren't that many contractors, or none actually, that can cast that accurately in concrete. So it's funny that engineers and architects are specifying concrete filled tubes when contractors can't deliver any other option. So, and I've been saying, if you can do a very complicated thing in concrete filled tubes, why not just the columns in warehouses, which is easy. So they're being used when the contractor simply can't do it. But they're about the same in terms of cost. So I'm still surprised that the warehouse industry hasn't picked up on it.
It's in my experience very. If you present this idea to the quantity surveyor, and he prices it without a program and the risk included, like a contractor would do, it will most likely fail because it's more expensive, and it will fall off the table in the planning phase. So we had this kind of response to several things that we tried in warehousing before, until we started to tender, simply to tender both, and let the contractor decide what works better for him, and also exploit the tender process to get to entice the tenderers to make it competitive. So they could choose the option that suited them better to win the bid, and that yielded interesting results. So maybe this is what I would recommend. One would need to approach this filled steel tube column idea. You must put it as an option on the bid and let the market decide, and it will. I'm actually curious now. Let's try that.
Cool. Let me know if you run into a new project, and we can work on it together.
Okay. No, definitely.
Cool. Yes.
Good. Any other? I think we're about to jump onto Leon giving some extra details on the project, and then I ask the question and send us on a very interesting tangent.
Yes, indeed.
But let's get back to some detail on the actual fabrication and erection process in terms of complexity or difficulty. Can you just give us a bit more insight into the actual erection process?
Yes, definitely. So I think for a typical person looking at this, there's really nothing that special about the roof. As Sebastian highlighted, the thing that really pops out about this was the way that we programmed this and the inherent health and safety benefits of using a lightweight product above everything else that was happening on site. As I also mentioned earlier, is we really tried to optimize everything as far as possible. I think even on this view that you see now, you can immediately notice how we've got bigger members towards the edge of the truss and smaller members in the middle, exactly as we require. And due to the specific member geometry that we are using for this project, for all our trusses and our girders, we ended up with really small elements, specifically the web members in the middle of the trusses and girders. So this was a bit of a challenge for us, just getting it to site in an undamaged manner. So we were involved there with the method statements to get the contractor to really buy into what we're trying to achieve and make sure everything got to site safely, undamaged, so that they don't have to take anything back or try and fix it on site. And as you can imagine, with a site of this size and everything that was happening on it, we also had to bring stuff in sometimes fairly early, store it on site, and quickly grab it as soon as it's ready. So there was quite a challenge for us in getting it to site and then also keeping it safe on site, just due to the economical design of all the elements. I think another area that is actually quite impressive is the steel penthouse on top of the roof, which is fairly unusual for a South African steel roof. Like normally you only have lightweight sheeting and a bit of insulation. We had this tank-style European roof with proper insulation, 2 layers of waterproofing, and then the penthouse portion, as Mercedes calls it, which is basically the plant room that is suspended above the entire facility. So on the outside here, you can see there's a rectagrid type structure where we have cooling towers and so on. But then the moment you go inside, this entire area was prepared as a typical plant room. So fairly high loading. I think a general loading of 3.5 kPa, but then specific loading under certain of the equipment as well. So all of this was a 6 small plate bolted with what were those bolts, Sebastian? The sunken. It was a really nice thing just to keep it flush and safe as well.
And they were countersunk self drillers, and there were IPE joists underneath.
Yes, yes. So I think that was fairly special for us as well, just considering the loading that went into that portion of the roof. I think
I just want to add something quickly. Leon, you said there's nothing special with it. What we made out of it was simple to build, but the starting point wasn't simple at all. If you look at the amount of services that are reticulated in the steel structure, if you look at the massive ducting systems that come in and out of the penthouse and distribute fresh air in the warehouse, they have 200 millimeter chilled water pipes coming in and out, and so on. If you look up, it is very busy.
Yeah.
To coordinate and optimize this loading and break it down to just a handful of typical trusses that were easy and repetitive to build and to erect, I think it makes it somewhat special. The simplicity that was at the end achieved is
absolutely
is part of the process.
Yeah. Don't get my statement wrong. I said for the casual observer, it looks simple, it looks like nothing special, but exactly as you point out here, but what went into that was actually incredible.
Yeah, that's in fact related to that was my second question. Since you guys did a built-up roof on this warehouse, I assume the roof was quite flat then.
Correct.
Yes. It's basically flat. We elected to collect the water in very, very shallow gutter-type channels along the girder lines and bring it down with a pluvial system. So the initial design was meant to be fully flat without these little depressions, which would mean that you have to build up about 150 millimeter overhead before the pluvia really kicks in. I thought, we don't want to carry 150 mil of water on the entire roof or half roof. So and this is just the depth of the purlin. So we just made a bit of trickery with the purlins. We create this channel to create the head for the pluvia and saved us a lot of loading to carry.
Yes. What was for a flat roof of this type? Was ponding or something of this type an issue at all?
It's not entirely flat, Leon. What's the slope? It's actually ridged between the
about 2 degrees
gutter lines.
I think it was 1 degree to the gutter line.
Yeah.
As you can see in this photo, so every 18 meters, what we did is we did a drop detail where we've got this long channel essentially, where we define the full bores. So any ponding that would happen would be in this area, and then close to one of the full bores as well to get off the roof. But as Sebastian said, it was a big concern for us initially before we introduced these channels, that if everything was blocked for some reason, let's say all the full bores in an area was blocked, you could get a lot of water. So that's when we started introducing the channels as well to really get the required head for the system to work, and to limit where this would be. So now it's on the girders all the time, in which we've got a better safety factor. There's a lot of accumulation that can actually happen, and the girders can take it. So you don't have to.
It's much stiffer. Yes.
Exactly.
And if there's one pluvia outlet blocked, it's a continuous channel. There's 4 others or 5 others or even more, 6 others.
Yes.
And then there's big overflows on either end. So it's actually between the architects and us, it's well thought through that the roof is not at risk to get damaged by floods. It's from this point of view, it's really safe. Because obviously the whole thing was a bit unusual for us South Africans to build a roof like this, but Mercedes simply wanted it like this. They insisted it's done in Europe because of the snow thickness. You need to have a tanked roof. And what is nice, you never need to worry about it lifting off in the wind. It's properly tied down.
Sebastian, what are you particularly proud of on this project? What do you think went really well?
I think, look, it was a turnkey job. So our WSP's client was definitely stocks. So the task number 1 was design the building. Okay, we can design buildings, no big deal. Okay, but design the building so we win the job. Okay, bigger challenge. So we cannot just design it and then tender it, you know. No, there's other engineers designing this thing as well for other bidders. So we got to win it. The trick with the program, I think, was contributing a lot to this happening, and we're actually quite proud of this. We already modeled the whole building in Revit, and we linked the program into the model, so we could actually run a program simulation in Navisworks, and picked up a few drastic mistakes in the program that we could correct in time, and this way save a lot of embarrassment. So that was actually a very nice application of a proper BIM delivery. And then on the steel side, you know, it's one thing to bid for something and win it, and then you win the job, but you have to deliver it. And we have to actually give credit to the entire team here. The lead of Stefanuti and the project directors that were involved, the architect and the whole supply chain. There were obviously there's the usual feathers that had to be ruffled here and there, but the whole team was working together very brilliantly to deliver the job, and it was actually delivered on time, and everybody is happy, and that's always something to be proud of.
Good. And
yeah, the structural steel worked like a charm. We had no accidents, no issues on the way. The steel is designed to be safely erected, so we wrote about this a little bit in our submission. Just drop in place first, secure, and then put in the big bolts. And that all worked actually very fine. So, Leon, what can we add?
I think one thing that I would like to add on that is the following, which I am specifically quite proud of. So because we were developing this whole building with our team before we even won the job and before we got the steel contractor involved, there was this requirement from Mercedes as a whole at the end of the project, but also from all our team members, that everything needs to be in the model for coordination purposes. Everything. So our steel model that you see here, this is not the steel contractor's model. This is our engineering model, and it is a LOD 350 steel model. So every steel element is in here. You can see the SAG system is modeled for the facade, for the purlins. The only thing that you won't find here would be bolts and nuts and some gusset plates. But everything as a whole was actually in there for everyone to work with. I think that was a really great success story for us as well, overall for the project.
Good. Well done. Emmanuel, do you have any final comments or questions?
No, not really. So why did Mercedes want 2 stories? What was the rationale? Just the
They
general
simply
question.
don't have space anymore. So the London plant has been coming on for decades now, many decades. And in order to build this building, we actually had to demolish an old building that was spanning in the one corner.
Okay. I see.
And that's also part of the reason why that first floor needs to take so much load.
Yes. Yeah.
The vehicles they only produce for 7 years before they move on to the next one. So this building will only be used in its current form for 7 years. And then everything gets taken out and it's got a whole new purpose. So it needs to be future-proof for the next 8 decades or more.
Hi everyone, my name's Ryan and a branch manager for our Fintra branch in East London. I didn't necessarily assist on this particular project in question, but I'm here to assist on Fintra's behalf and Monit's, who heads up our technical department.
Great. So you guys will be able to give us a little bit more insight into the cladding components of this project. Fantastic. Monitz, you want to say hi?
Hello, everybody. Emmanuel, Denise, I've met you. So, Tulani, good to meet you. My name is Monitz Beneke. Hope the audio and the video is okay. Right. Why I've asked Ryan to join is I was involved from the technical point of view right in the beginning of this project, 2017-18, and mostly involved with a lot of testing, etc. I'll discuss that a bit later in your questions. Anyway, it's Fintra, technical department, and Ryan's backing me up because I left the company for about a year in the period where the body shop was being concluded, and Ryan was actually up on the roof inspecting. So if there's anything that I can't answer, he's there as a backup, just for continuity of the process.
Can you just give us a brief description of what the cladding is that was used on this particular structure?
We started, the first brief was looking at the roofing envelope, and the cladding component there was a concealed fix, a product called Saflock 700, which is conventionally used as a clip-on or as I said, a concealed fix product per se. The difference in this project was that the sheeting was essentially being used, and it's probably not the correct engineering terminology, but as a shuttering or a weight carrying system. So the sheet was essentially turned upside down, inverted, directly fixed into the purlins, and then on the top section of the roof there was a built-up system with a waterproofing element that finished off the roof. So my initial involvement was definitely making sure on the original part of the project, but obviously going through into the body shop was to make sure that we have good stability on the sheet in that specific application. So to answer the question, it is just give you the exact specification. It was Saflock 700 inverted application. It was manufacturer roll form from 8mm G300 steel, and was color coated with Color Plus in a C spray finish, and that's what you basically seeing initially there as the guys are installing it onto the steel framework. The cladding was a double skin system where the outer skin was a industrial 7 profile in a aluminium finish. So just a plain silver metallic coating finish, industrial 7 900 series aluminium, and that was in 8mm material. Wedged in between was an insulation, fiber insulation product, and then on the inner wall was a Wideck 760 Wideck profile, so it's a box rib profile, also color coated C spray, and that was gauge material was 53 G550 high tensile steel that we used there. So a double skin aluminium outside, Color Plus material on the inside, and then sandwiched in between was an insulation system.
Okay, can you give us a little bit more detail on the actual installation process in terms of its complexity or innovativeness? What do you think makes this stand out from other entries that may be in a factory and warehouse or cladding category?
On the cladding, needless to say, it's not something that you often see, but it's also not a out of the ordinary detail when we talk about the double skin system with the also creating a cavity with the insulation. The first out of the norm was the fact that a conventional Saflock sheet was now being used as a inverted load-bearing member, and all the goodies that went in between or from that point upwards was actually quite interesting. Obviously, our role initially, or our brief initially, was just to have a look at the sheeting, the fixing methodology into the purlins. That I know on the initial section there were quite heavy gauge sections that we had to draw into, make sure that we had sufficient clearance, etc. We had to look at deflection, so on and so forth. So we did testing with the engineers, with the subcontractors, as well as with the contractor, with them attending. From there, later on, we started looking at the actual built-up system as well. Although we weren't part of the specification, it was more a case of a collaboration between the different role players. When you look at the professionals, us as the suppliers, the subcontractors, and the contractor, to make sure that the system would work and was in accordance with the required spec from Mercedes-Benz. So I think, to answer your question, the short answer is just the fact that from a cladding point of view, on the roof itself, it was being used outside the normal realities or realms of what the product is normally used for.
Emmanuel, Tilani, do you have any questions or anything, any comments?
Yeah, I'm curious to see. I know you guys may not know the answer, but what are those big precast beams there with big holes in them? They're not. I can see they're not steel.
Well, let's maybe just have a look at it again. I have no idea, Ryan. Maybe.
Yeah, I was going to ask the same question as well. I thought it was. I thought it was still castellated beams, but
yeah,
images.
Someone took a lot of effort.
Concrete castellated beams.
Well, I just want to see if I can try to find the project again to just share those, because I had closed my screen. Let me just skip to the next question and we'll come back to that. How would you say that this project really demonstrates the benefits of steel as a material?
Well, again, it proved to us the taking a flat sheet off a coil and profiling it into a specific geometry, the strength of material in steel. The roofing that we used here, yes, for what we used to, 0.8 millimeter thickness is quite a heavy gauge. But from an engineering point of view, Manuel, you'll know that 0.8 is nothing. And just the fact that you're taking a Saflock sheet in this instance, forming it into a specific geometry and actually being able to span, I mean, the J building, which is not adjudicated here, the spans were very close to 3 meters. And the deflections that we found there were minimal. And believe me, it was tested and retested and sandbagged. And so in terms of the benefit from steel, it's, again, the short answer is the strength in your gauges available. The other thing that I'd like to mention is just the clever, way that the built-up system was actually designed. Yes, although it was according to specifications from Europe, it's amazing that you can, again, in collaboration, end up with such a system, basically done in reverse. Everything we do on a day-to-day basis is everything gets underneath, back between the structural steelwork, and now it's just been turned upside down, which to me just opens up a lot of new ways of thinking about this concept. Ryan, I don't know if there's something that you would like to add without putting you in the spotlight here.
Yeah, I also found the application to be quite
I think
innovative.
From our,
yes,
on the cladding side.
How long were those sheets? Do you remember?
On this specific building, I won't be able to comment. I actually didn't inspect this one. So, Ryan, if you're still online, if you could maybe just give us an idea.
Yeah, the cladding on the external cladding on the aluminium was, I remember, being around 13 meters. Sorry, actually they went up to 16 meters. We had to actually get in an abnormal load and arrange permits and that to transport these exceptionally long sheets, which I remember spanned up to 16 meters in the Industrial 7 profile.
Yeah, that was for the cladding and the roof sheeting.
The roof sheets. I was more on hands on the logistics building, which is just out of sight in this picture. But on this building, I can't remember the exact cutting list, but just by the looks of it, there you're probably looking at, I reckon they were around 20 odd meters in span, rolled on site in Safflock profile. Yeah,
so the roofing wouldn't have given us such a big issue because most companies would have a mobile unit that can go to site and produce on site. As Ryan mentioned, obviously on the cladding, it now becomes a bit more of an issue because you can roll the sheet as long as you want, but you need to be able to put it on a vehicle and transport it safe and sound.
So, what are you most proud of on this project, gents?
Say again?
What are you most proud of?
Okay. Well, Denise, I think from my side, definitely the fact that right from the beginning, we were approached by the professional teams. The concept was out there. The spec was given, but it wasn't just it shall be. It was a huge collaboration, really. And we spent a lot of time with the guys. One of the engineers that, the mails and the communications went backwards and forwards, and we were basically learning from testing from on site and adapting as we went along. So the answer for me, what I'm most proud of, is the fact that it was a collaborated effort to get an excellent end result, and something that's quite unique, I would think, in the South African market.
Any questions to Lonnie and Manuel before I hand over to Ryan?
No, not from me.
It's just one question. I mean, what was the reason behind inverting the sheets?
Well, it was when you look at the underside of a Safflock sheet, it gives you a very you'd be more familiar with the term clip lock. So if you just imagine a clip lock sheet in section, turning the sheet upside down gives me a very flat, uniform surface to actually lay the bats on top of, as opposed to installing conventionally, and then you limit it by your 200 or 230 millimeter spacing. So turning the sheet upside down from spacing from laying the bats and applying the torch on number one, and then number two, this was something that we also chatted to Mr. Dennis White about, was the strength of the profile inverted. That was a little bit of untreated grounds. So to answer the question, yes, to give you a uniform platform to work off, but then also considering the strength of the material, definitely in terms of the direct contact with the ribs and the strength of the ribs onto the support structure.
Okay, that's good enough. Yeah.
So actually,
following
on from Tulani's question, how flat was the roof?
Ryan, that was about 2-3 degrees. I'm just working off the inspection that you did.
Yeah, very shallow. Yeah.
Yes, yeah, virtually flat.
Great. Ryan, you want to let us know what you're most proud of on this project?
I think from just watching it from our side, being based in East London and helping, so the obviously Impact Engineering is a firm based in Durban, and me being here in East London, just assisting Durban. The roofing engineer who's in Durban works closely with our Durban branch. So I was here just trying to alleviate the miscommunication that sometimes comes into play with being so far apart. And I think from our side, a proud thing would be for me is just how well and organized everything went on, from site rolling to deliveries to arranging coil. It's quite a lot that goes on behind the scenes, and especially not being based here from Durban, like I said. I think it went really well in terms of the completion dates as set.
So last question from my side, and then if the judges have got any more questions or comments, they're welcome to let the gents have them. What would you say is the most technically impressive aspect of this project, in your opinion?
I think it's the spans that we achieved. That for me was the most technical challenge. By all means, I mean, we had no other option, so we had to make it work, or then alternatively look at some other type of profile. But 3 meters, I mean, from architectural engineering point of view, I'm sure you gents will know, and you Denise, that spanning 3 meters is for me is quite a technical feat within deflection criteria or deflection limits. That I was quite chuffed with that.
Ryan, anything to add to that?
Another thing would be something that we would say on the technical side is just getting those long industrial 7 sheets delivered. It's quite a thing to deliver a 16-meter sheet, as well as the flashing details that went on some of these on this building. There was quite a hefty and broad range of different detailed flashings, which a lot of, I think, people when you walk by a building don't even notice, but when you're actually designing and measuring flashings, getting them bent and delivered to site from Durban without being scratched and damaged is quite a technical feat from our point of view.
But, Denise, just something,
yes.
Sorry, just something that I forgot was, and Ryan mentioned it to me this morning when we had a quick chat, is the fact that when you look at the cladding section, with the outer skin being aluminium, we could then promote using a color coated product in a normal AZ150 coating, and still be able to get between 15 and 20 year material warranties right on the coastline. So again, from a technical aspect, it's just, you know, considering the use of aluminium, bright silver aluminium on the outer skin, it then opens you up technically to start using other materials, which is more protected, which is slightly more cost effective, and still be able to get your well, I think it was 15 years on the, well, it was between 15 and 20 years on the system per se. So I think it's quite good, because it's saving the client on the financial side as well. So just being clever technically about what materials you use in what combination.